Still coming out.
So what's the plan for next week?
So next week we're going to get into some of the other kind of more advanced things. So we're going to talk about how do you adapt this technique, how do you adapt artificial neural networks to regression tasks. We're going to talk about this general pattern that exists that makes it actually very, very easy to find and calculate the gradient for arbitrarily deep networks. And we're going to get into, again, kind of talking about a little bit of how you might diagnose like how deep your network needs to be and all that kind of stuff. It's very, very similar to other stuff that we've done.
So what we talked about actually deep learning is when we come across like two hidden layers, and that is.
Anytime you have more than one hidden layer, you're talking about deep learning, basically. So, and in some really extreme cases, you'll have hidden layer, or you'll have deep networks that are like hundreds of layers deep. But there aren't many applications that require this. So we'll also have to talk next week about some of the other activation functions, right? Like the ReLU or rectified linear unit.
So far we've done this back propagation. There's something also called forward. Is it the same kind of thing? Forward.
So this I thought would have been kind of clear just from the terminology. So when we take inputs and we calculate them into outputs, that's called forward propagation. So anytime that you're taking an input and you're calculating an output, you're doing forward propagation. Backward propagation is, or back propagation is how you train your model. Okay. Let's do a new one. And I guess just to kind of show you guys sort of how this is like really similar to logistic regression, we'll even do this on the same kind of data that we would use for our logistic regression example.
Can I go a quick toilet?
Sure. Okay, so we'll simulate the data.
I think Jiben is here.
He is. I'm also making him wait. So I'm making him wait. He will have been here for an hour by the time I get to him, and I still have to do Mabuk's tech test before I leave today at 6. So I've left myself like 2 hours to do it. Oops. Let's see. Okay. One. Which is going to be. Okay. So there's our usual data set, right, that we're going to have to use to train a model to classify. So now let's make some functions that we're going to need. So we're going to have to define our softmax function. And NumPy actually already has a hyperbolic tan function. So that's going to be, I'm not going to have to do anything with that. It's already taken care of for me. Okay, and now I'm actually going to define a function. You can call it feed forward, you can call it forward propagation, whatever, but this is the function that's actually going to carry out the forward propagation. So this is going to take x, which is our input. It's going to take in a w1 and a b1. So for a number of reasons, I actually do my bias weights separately for artificial neural networks. Just because if you guys think about how this would go, where you kind of have to take the output, stick that into the next function, take the output of that, stick that into the next function. If you were to handle your bias weights via a dummy variable, you'd have to have this extra code that figures out a way to like stick a dummy variable into that output at every layer, which is like hard. So rather than dealing with that mess, I just actually go ahead and separate the bias weights out. Okay. So what this is going to do now is this is going to calculate the hidden layer. I'm just going to call it Z instead of Z1 or whatever. I guess actually, you know what, to just go ahead and be consistent, I'll just go ahead and call it Z1 so that this can stay the same for, future things that we're going to do. So I'm going to apply the hyperbolic tangent at this layer. And this is going to be the matrix product of X with W1 and then plus B1, which is our bias. And then our output is then just going to be the softmax of Z1 with W2 and then plus B2.
What is B2 again?
It's our second bias. So our bias weight at the second layer.
Ah,
Okay?
So W0.
Yep. But we have to have two W0s, right? Because we have two
Yes.
sets of weights. Okay, and then we go ahead and return. And because I'm going to need the Z1 value to calculate my gradient, then I'm going to actually have this returned as well. So I'm going to do it like this. So it's going to return both the hidden layer value and the prediction value. Okay? Still just need the cross entropy. Went over, and the n can literally just be the length of y so that I don't have to pass in an n. And then times. Oops. Okay. We'll find our classification rate. Okay, so I think those are all the functions we need. Okay, so now we're going to build the model, or kind of construct the model. So I'm going to set Q equal to some number, just to kind of pick a number.
Random, right?
Yeah, like I'm just going to pick something. So 4 seems like a good number. This is the thing that I would diagnose later. So we're going to say Q equals 4. Then we're going to define W1 to be D by Q. And we don't need to worry about it being D plus 1 because we're actually separating our bias weight out. It doesn't have to be part of this anymore.
So when we create our fees and all that, we shouldn't include the dummy variable anymore.
Yep.
Okay.
Not for neural networks. And then if we have Q neurons, then we have to have B1 has to be a vector of length Q, right? Because it has to feed forward into each thing. Okay, and then we have to have W2, which now has to be Q by K. And then B2, since we have K nodes at the next layer, has to be K. Okay, so this is kind of the model. This is literally it. Now we just have to train the model. Okay, so as per usual, make a list to contain our errors. We decide on the learning rate, which, let's see, good starting point, 1,000 APOCs. Now we go for T in range APOCs. So we're going to first calculate our hidden layer and output values using just our feed forward function with our current weights. right? So this takes x, w1, b1, w2, and b2. Okay. Now we're going to want to calculate and store to make sure that this is working correctly, make sure that this actually converges. Our error values with that. Now we don't just simply have one equation though for updating our weights, because we have two sets of weights that need to be updated. Okay? So we're going to go ahead and update W2. And this is still the same formula, right? So it's the learning rate times 1 over n times our gradient, which we calculated to be z1 transpose, or let's see, z1 transpose times p minus y, right? Okay, then we have to update b1, which looks like this. So if you guys go back and look at the formula for the bias weight, then for the bias weight, actually, the value, like the z value, or the, oh no, sorry, not b1, b2. Then, so like z0, right, is kind of that bias weight, right? But it's actually just always equal to 1, right? Because that's what a dummy variable would be, right? So instead of being a matrix product, it actually just ends up being a sum. And it's actually what would be kind of the sum on all of the, let's see here. Yeah, so it would be like if we summed up all the rows. So what we end up doing here is we do this same gradient that we would get for the other thing. And then we sum over axis 0. And this ends up producing a vector. So this would be a matrix that's n by k, but we're summing up all the rows. Well, we're summing down all the columns, I guess, and so we would end up with a vector of size k, which is what B2 is supposed to be. Now we update W1. And so this gradient is right on the board here. So, oh, and actually, I'm gonna do this. Because that's actually the gradient. So this is going to be 1 over n times matrix product of x transpose with this other thing. So,
So it's p hat minus y.
Yeah, but there you said it's W2.
Yep.
And you write W1.
because I'm updating W1 now.
W2.
Oh, I wrote down W2 there, didn't I?
Yeah.
Sorry about that, Jonas.
Well,
So this is the gradient with respect to W1.
and everything is W1, right?
Nope, this is still W2. All right, so then we're gonna have to do p minus y, or product of P minus Y with now W2 transpose. And then this multiplied by, just element-wise multiplied by 1 minus Z1 times Z1.
Jeremy, something else.
Hmm.
The X transport doesn't multiply all the other bracket. Why you put comma?
Yeah, no, it does.
Why you put comma instead of bracket?
So X transpose is being multiplied by all this.
Yeah.
Yeah.
We don't need to put in the bracket all of it.
Well, it's the other argument to this
Oh,
matrix
okay.
multiplication thing.
Okay.
So Python knows.
No, for the priority. I mean, for the priority,
Oh,
the order.
Mm,
No.
no, because so what's going to happen is we have P minus Y, which is N by K, right?
Yeah.
We have W2 transpose now, which is K by Q, which means that this is going to spit out an N by Q
Yeah.
matrix, right? Then that's going to be element-wise multiplied with this thing, which this is N by Q. It's being element-wise multiplied by something else that's N by Q. We're just doing 1 minus that, so it's going to broadcast that to everything. So this thing's going to be N minus Q, or N by Q, and then we're element-wise multiplying two matrices now that are N by Q, right? Now we have X, so this whole thing here is N by Q. Now we have X, which is N by D, but we're taking X transpose, which means that that's now D by Q,
So we can do it like.
or sorry, D by N. So
Yeah,
X is N by D, X transpose is D by N. We're matrix multiplying that with the thing that's N by Q. We're going to end up with a D by Q matrix, which is exactly what W1 is supposed to be. Yeah, so when in doubt, just figure out what your dimensions look like.
Jeremy, I'm just a bit I didn't get the formula for W2. Where did you get that formula from?
We already derived that on the board, so if you have the video, you're going to have to go back and just look at the video.
Okay.
So, and remember, it was just like the gradient for logistic regression. It's just that now instead of X, we're using Z1 because that's now the input.
Yeah.
Okay.
Actually, it was the beginning.
Yeah.
Now we got to update B1. So then we've got this guy. Which is going to be the same thing. And we're going to sum this guy over axis 0. Okay. Then at the end of all that, we're going to plot J to make sure it's a good size. And all right. So I've been in a rush. Hopefully I didn't screw anything up here. Oh, looks like I did. Y is not defined. Oh, that's right. So we got to do some of our data prep real quick. So this has to be N by K. matrix. So we have to do this thing to one hot encode our target because it's actually a vector, but we need it to be an n by k matrix, right? So let's go ahead and try that again. All right, so not really converging very quickly, and it's like really not converging quickly, so I'm just going to bump that up a lot. Actually, we should reinitialize our weights. And then do it again. Okay, still not really converging. Maybe we'll be a little more careful now. Oops, so maybe that's a little too high because it's starting to go up again. So let's go. Maybe let's up our number of APOCs here. Oh, whoops, I didn't reinitialize my weights. This might not work. We'll see. Yeah. Looks pretty good. Okay. So now, let's go ahead and report our classification rate. So about 96.4% classification rate. Probably could do a little bit better. It looks like we're actually still seeing some, it's not really as flat as I'd like. So if we had more time to let it train, it probably would do better. That is one thing, is that these are actually slower to train than a logistic regression. And then we're going to want to just visualize the learned decision boundary. And you guys will see that this is actually quite nonlinear. So we'll go xviz, which equals let's see, I think this last time we would have been like -66. We'll do that. Then we're going to get pviz. So we're literally just going to feed xviz into our trained model. Right? And then we're going to oops. And it's going to be a whole shitload of points. Oh, object has no attribute. Oh. So I forgot. This puts out both the hidden layer value and the output or the prediction. So this is actually outputting a tuple. So if I only want the prediction value, I have to kind of stick at the end here this thing that tells it I only want the last thing that you're outputting. Right? Because what this is doing here, where I'm saying you output Z1 and P, is that this function is actually outputting a tuple. Right? So if I just want, I could do this one of two ways. I could do it this way. Oh, fucking hell, come on. X and Y must be the same size. Why wouldn't they be? So let's do X viz shape and P viz shape. Yep, so so those are the right shapes. So what do you want from me?
D was supposed to be 3. He's mocking us 2.
No, D is 2. That's fine.
The other one is
That's how we're able to plot it like this.
Uh,
So D is definitely 2.
So why would be this is 3?
It wasn't previously 3. It was 2.
I am sick. Okay,
Oh. Hang on. Hey, what's up? Oh, hello? Good, how you doing? I am. I'm still actually down in the classroom. I'm trying to teach these guys how to build a neural network before the weekend so that they can do their weekend assignment. Yeah, so what's up? Okay. Uh-huh. Yeah. I don't really have anything that I'd want to share. Yeah. And I think, I don't know, Mahbub kind of has his like final project, but I don't know if that was actually, like it was good enough to graduate, you know what I mean? But like I don't think I'd want to like hand it in to a recruiter. So when's the tech test due by? Yeah. Okay. Okay, I can do that. Okay. Sounds good. All right. Yep. See ya.
that was Daniel, right?
Yeah.
Yeah.
All right. Let's see. I don't see why this wouldn't be working because these are the right size. These are definitely the right size. So we've got 30,000 and 30,000. So then when we do
30,000,
wait.
2L, and then 3L.
So when we do XViz 0, and we check the shape of that. Oops, except we used curly brackets for some reason. All right, that should be a vector of length 3000. This thing also should be a vector of length 30,000, I mean. And then when we do p viz argmax on axis equals 1, and then take the shape of that, that should also be a vector of length 30,000. Yeah, so these are all the same size. What do you want from me, Python? All right, well, I don't really have time to mess with this, but I'll just go ahead and V2. So it's even saying like y and x must be the same size, which means that it somehow is. Oh, there it is. Wasn't a very helpful error. God damn it. There we go. So this is how the model is chosen to divide up this space. Nice. So you can see, not very linear, and actually maybe we'll go ahead and let's bump that up even higher. So in this case, it actually might be worth starting and like restarting again, just because now the difference is we have so much more complexity in our model. This is not a strictly convex function anymore, right? Our objective functions are no longer strictly convex, which means that we actually can possibly end up in local minima, and we have, there's no guarantee that we have found the global minimum.
What is your classification already? What's out then?
If that's actually one thing, and this is another thing that just like really sucks, is that that might be one thing that might just like push us over the edge. It might just be that we have to just try again and get kind of just like a lucky shake.
Mm-hmm.
And maybe we'll have some way of just kind of recording like what were our initial weights so that we can figure out like what was kind of the best place to start. So which thing actually led us to like the best max or the best minimum. Because if you start there again, the gradient is the gradient is the gradient. There we go. So that's kind of. I still might have a bit too high of a learning rate because you can see that there's like a part there that kind of bumped back up. But let's see if this is any better.
No.
So nope, a little worse, actually. So again, just kind of started in a different place. So got to a different minimum, right?
No.
So now it looks like this. So we can try again. So let's again reinitialize our weights. And then let's try, here, let's actually try and back this off a bit. And just try with more training epochs. Lower learning rate.
If you fall into a local minima, your classification rate should be way worse, right?
Depends.
Yeah.
That's the thing, we have no idea of knowing. These functions now are so complex, we don't really have any great way of knowing. So we could have ended up falling into a local minimum that's not that much worse than the global minimum, or it could be way worse. We don't know.
Yeah. And we don't know how many minimums, potential minimums we have here.
Nope, no idea. But there are other techniques, way more advanced techniques, that people use to try and solve this problem. So you guys actually might, don't think about this now, don't worry about this too much now, but there's actually another technique that's called like the particle swarm optimization technique, which means instead of just dropping one ball and then like seeing how it goes, like where it rides the gradient down, we literally create like a swarm of balls and we keep track of where like all of them go, and we see like basically kind of like what, you know, what minima are there, because we hopefully have found all of them if we literally just flooded the whole function space with like this swarm of particles. And then we figured out, based on that, like what was the best one. All right, yeah, what's funny is that looks like that even could still go down farther. That's the thing, sometimes these take a lot of training APOCs. Right, and you can see too, we do not see the same like journey down every time, right? Like I'm starting from, I'm having to kind of go over different features of the function every time. So did better that time, we're at 97.4%. So there we go. That's actually not so bad.
Then in terms of regularization and all that, do you even know if you need to regularize, or if it just a problem is that you found a local minimum?
You still use the same. So what you would do in that case is, again, you'd probably want to set a seed.
Yeah.
To see, you know, so that you're kind of starting from the same place, and then you'll want to check everything else. So, and you'll still run the same diagnostics to see if you want to regularize the model. You can actually, this I think is quite nice. So all you do is that for each one of these gradients, you then add your regularization terms to your gradient. Make sure that you actually would like enclose that in. So like if I want to do like L2 regularization here, I would have to make sure, because that's part of the gradient, that I'm doing something like this. All right, so like, right? And then I actually can choose, because you guys remember I told you that you have the option of regularizing the bias weights or not. It's actually very easy to choose that now, right? Very, very easy for me to decide whether to do that or not, because here I'm not regularizing the bias weights, and here I am. Right, so I can kind of choose like whether I want to add this to the gradient for the bias or not.
And then for the W1 and B1, you do the same thing, right? You plus lambda 1, W1.
Yep.
Right.
So the gradient is still the same, right? Like I'm just choosing to sum over an axis in this gradient, but the gradient still is, I use the same gradient to update B2 as I do W2. So it's just that, again, if I want to choose to not regularize the bias weight, because that's an option. Some people say don't regularize the bias weight. I can just simply choose to not add this regularization term in to the gradient.
You could pick different values for lambda 1 and lambda 2, right? Or have to be
Oh, sure. You'd still do the same diagnostic to do that.
I mean, never like the lambda for the W2.
Oh, yeah.
Different to the lambda for the W1.
Yep. So if I'm going to do both, like if I'm doing like kind of an elastic net thing, that's why I even called it like lambda 2, right? Right. So like this. And then again, I can choose whether I'm regularizing the bias weight or not by choosing to include or to not include those terms in this.
So now we need to make a for loop for the D as well to find the ideal D.
No. Not D, but Q.
The Q, sorry.
Yeah.
Yeah, for the Q.
D is decided for you by your
yeah,
data.
no, Q, I mean Q.
Yeah. Yep.
More or less we do the same as lambda.
Yep. So just as before, you'll do the same kind of diagnostic there. Okay. Yeah, and you may find, because I actually do find, so like there are still parts where this goes up, right? Which would indicate, so there's this like mathematical proof that's out there. I'd have to find the research paper. It's because I don't remember that proof off the top of my head. But it proves that as long as your learning rate is sufficiently small, you actually should see this curve decrease with every iteration. So this should be a strictly decreasing curve if you have a sufficiently small learning rate. So the fact that we see that this goes up means that I actually could stand to have a smaller learning rate.
Okay.
Which actually, oh, I don't even think I made it smaller. I think I meant to do that. So,
If you want to know something, change that.
yeah. But anyway, yep, that's what we have now. And you can see these are definitely nonlinear decision boundaries that are being defined. So this allows the model to actually fit more complex decision boundaries than just a multinomial logistic regression, which does have to define straight line decision boundaries. So, but yeah, that makes these things actually really, really great when we fit these to regression tasks. They're excellent at function approximation because they just, can conform to so many strange shapes. Okay, so this should definitely be enough code. You guys will see, actually, it was almost painful for me to write this shit, because this just looks like an awful lot of stuff, an awful lot of mess. I don't really code up neural networks like this anymore. But, this was to just show you guys the solution off the board that we just derived. But if we actually, here, let's see if I can find one. And before I do anything else, so I don't forget, because I do want you guys to have this over the weekend. Where are you guys? Over here. Let's see. There you go. So we're going to have to do some work to actually see the math behind this, but let's see if I have one from before when I was teaching like Mob over here. So yeah, this is for a regression task. But so here's like a deep network that has a bunch of layers, right? And you can see though that the code for calculating each gradient and updating each layer is actually like pretty compact. It's pretty concise. So there's actually like a pattern, like a set of 3 formulae that I'm going to derive for you guys to show you that it's actually not bad at all to calculate these. Oh, beautiful. Look at that thing. Now this is actually a pretty interesting feature as well. So I use the rectified linear unit activation for this, which we'll go more into what that actually looks like and everything, but it's like still kind of linear. Like it's not a curving, it's not strictly linear. People still refer to it as a nonlinearity, a nonlinear activation function, but it's not curving in any way. Like it still is straight. So as a result of that, you can see that it actually does create a function that conforms to this curving trend. But if you look closely at it, you can see that it's like straight from here to like here, right? And then we have this like bend, and then it's straight from here to here, and then we have a bend again, and then it's straight from here to here, and then we have a bend, and then it's straight from there to there, and then we have a bend, and then it's straight from there to there. So it kind of like finds a way to sort of like, again, it looks like a bunch of broken sticks, right? It's like you kind of have to like bend or kink this like straight line so that it more or less conforms to this pattern. Yeah, pretty good R-squared, 0.988. So yeah, these things are actually really excellent at function approximation. Let's see if I can find a classification one. Again, I didn't name any of these for ModBoober-G, but I shouldn't have done that. But oh, here's a K-means example I did for those guys. But unfortunately, like those guys, I'll have to just cover that stuff in training with you guys. Let's see. Oh.
Your code looks completely different.
Yeah, that's because it's a totally different approach. Very, very iterative. It's actually a totally different type of thing. So this is a thing that everything that I've shown you so far still fits into a thing where you solve this with gradient descent. But stuff like Gaussian mixtures and I must have used the same example before. Oh yeah, look at that. That's beautiful. Oh, this is like one of our first examples. So this is actually just with one. I'm using a hyperbolic tangent there. So you can see this actually does a very nice job fitting to that curve or fitting to that trend. Very, very nice. Can you guys even see that actually?
Mm-hmm.
Yeah. So these are actually great for function approximation.
That one, I saw that you put the atomic variable in the X file.
Let's see. This is our little exercise thing that we did. You saw that I did what?
That you put the dummy variable in the X.
Did I? What number was that? Shit, I don't remember. Oh, this was like kind of a more advanced example. We did okay then. We had like a saddle. There's got to be a. Oh yeah, I took two different approaches to this actually. One of them worked a tiny bit better. Anyway, there's got to be something where I did classification. Couldn't have deleted all those. No, this was for you guys. 11, 12. Oh, again, I already just opened this one. Yeah, I should have labeled these. Oh well. 16. Yeah, this is that one.
We've seen that before.
No, this one has the dummy variables separate. Shoot. All right. Well,
I must have seen the big dice.
I thought I might have had like a deep network example of classification, but I don't. Well, they're all for regression. Because ModBoober and Jeevan and I have been talking about this kind of stuff more recently. So, but yeah, you guys actually should notice here. So for this initial one, this like the derivative with respect to H6, that I actually do kind of define as this thing that most people will, without explaining where it comes from, most people will just like, oh, it's this like delta thing, right? Because it's like your output minus your target, right? The difference between your output and your target. I'm actually going to show you where this comes from, though. This is actually the derivative. It's not like just a thing that that sounds good, right? But then after that, we just get the same thing that comes up over and over and over again. So we have that the derivative with respect to this hidden layer is the derivative with respect to h at the next hidden layer times the weights for the next layer transpose, right? Then the derivative with respect to h at this layer is the derivative with respect to z at this layer, element-wise multiplied by the derivative with respect to the derivative of z with respect to h. Which for the ReLU, that's actually all there is to it. That's all you have to do to code it up. Then the derivative with respect to the weights at this layer are the matrix product of the hidden layer, one layer down, and the logit at this layer. And if you guys look, this is actually the pattern that emerges in all of these layers. So it's actually like quite concise to code up for each layer. And you can't necessarily just throw this in a for loop though, because depending on what your activation functions are, like this looks just a little bit different with each one. This actually does have some repetition to it, because you can see that what I did is I actually used the rectified linear unit at one layer where we had 6 neurons. So ReLU with 6 on a 6 neuron layer, and then have it all collapse down to a single neuron where we just do like a linear output, just like straight linear output, no activation function, and just repeat that over and over and over again. So like another 6 unit layer with ReLU, another 1 unit layer that's just strictly linear, another 6 unit layer with ReLU, and then another final output layer that's just linear. But even though everything's linear, we actually were able to fit this nonlinear hypothesis quite closely. But we just have a bunch of like linear segments that we've like stuck together. So yeah, unfortunately, I think I kind of in an attempt to sort of clean up this folder, I like ended up deleting a bunch of stuff. So deleted some of my other examples of like, or all of my other examples of like deep classification. So yeah, this is stuff we've done. So yep, bummer. Okay, that's all right. We'll make one. That's probably why I didn't think anything about deleting, because I was like, I can make a new one anytime I want, so whatever. But all right, so we are now 2 hours over time. So
Actually 3 hours.
are we? We're supposed to be out of here at 2:30. Yeah. But now you guys should have enough to go on to actually fit an artificial neural network over the weekend. So those are your tasks. So fit an artificial neural network to your data. And just recall, so like the part here where we've got like element-wise multiplication with the derivative of your activation function. So you guys will probably remember that when we had our activation function as the sigmoid, that this actually is equal to, if you take the derivative of this, so this is equal to sigmoid times 1 minus sigmoid, right? You guys probably remember us calculating that derivative. So in that case, if you decided to use the sigmoid activation function, then you just replace this with your sigmoid derivative. So this would end up looking like this. You'd go right, all this would be the same. But now, instead of element-wise multiplying everything by our derivative for the hyperbolic tangent, we do the derivative with respect to sigmoid. Right, so if you want to switch up your activation function, that's fine. All you have to do is, well, one, literally switch out the activation function in your feed forward function, right, that actually calculates your inputs into outputs. And then you'd have to just replace this part, which would have your activation derivative, with the appropriate activation derivative. Honestly, I wouldn't expect to see necessarily like vastly different performance between like a hyperbolic tangent and a sigmoid activation. I would just expect to see that your hyperbolic tangent would train a bit faster, right? It just won't take quite so many training epochs to get the same result with your hyperbolic tangent. And that's really kind of it. So we haven't really looked at how do you code up the rectified linear unit, how do you code up the derivative, what is the derivative, like we haven't looked at any of that stuff. So I wouldn't expect you necessarily to tinker with that over the weekend, but you can at least tinker with those two activation functions, and you can also tinker with the number of hidden units you have, right? The number of neurons in your hidden layer that you have. Kind of a good rule of thumb would be to start with at least as many as, so the Q, you want Q to be at least as large as D, right? So if you have like 9 features, you'd want at least 9 hidden units. Because, yes.
We need to one put the code again on the all the.
You treat the data exactly the same. You prep the data in exactly the same way.
Yeah, create more features.
If you want. You still actually could do a combination of making an artificial neural network and engineering like polynomial features and all that kind of stuff as well. There's nothing that says you couldn't engineer additional features if you're doing an artificial neural network. But yeah, I mean, at some point you have to stop going a little bit nuts and just like build a fucking model, like because the options truly are limitless. So at some point you just have to settle down and build something.
Right, so the task is to put everything to validation test, but also do diagnostics.
Yep.
Okay.
As much as you can, run diagnostics to see. You should find more easily that you are actually in a high variance situation. And then once you find that you're in a high variance situation, see if there's some amount of regularization that, that's perfect and smooths it out just enough that you're, that you're able to get a good result. Because it might be the case that, like, say, going from, like, maybe, 9 hidden units is fine, and, like, 12 is fine, and then 14 is fine, and then, like, 15 is too much, right? Mm-hmm. And so you want to, like, now there's kind of this question of, do you go back to 14, or, is it that decreases your variance too much or increases your bias too much, and that you're maybe better off staying at 15 hidden units and then regularizing a little bit instead of actually backing all the way off to like 14 hidden units, right? Mm-hmm. So you get to where there's actually like a lot of ways that you can kind of, check things out or combine things. And that ultimately leads to something that I still am kind of debating, like whether or not I want to show you guys. I never showed this to Mabu or Jeevan, but it's actually called grid search. Because the reason I don't love grid search, and the reason why people in general don't love grid search, is that it's a very brute force approach. It's a very, 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 like, nothing clever. We're literally just trying everything. Like, it's a total shotgun approach. Where what you do is you have all of your hyperparameters, right? So you have like your regularization, your lambda 1, your lambda 2, your like number of hidden units in your layer. So assuming you're not even going to mess with the number of layers, but like the number of hidden units in your hidden layer, and all that kind of stuff. And you literally write like a for loop, and usually you're just going to end up writing like a bunch of nested for loops where you loop through like all the one for loop that goes through the values of lambda 1, one for loop inside that goes through all the values of lambda 2, and one for loop in that goes over some range of hidden units, or some range of Q. and you literally just try every possible combination of like all your hyperparameters and just see like what gives you the best thing.
That sounds like a whole loop that would be running for quite
Yes,
some
it's
time.
incredibly slow to
Yeah.
run, which is why people are sort of like, there's got to be a better way. So it's almost one of those things that like, if you did like totally optimize the model and come up with like this best amazing version of the model, but you had to use grid search to do it, it's like almost kind of a shame. You know, it's almost like, oh, I couldn't come up with anything more clever, so I just did grid search. Like, you know.
Yeah, because you still have your epochs there as well, and lambda, God knows how many values you want to put in lambda as well.
Well, your epochs and your learning rate, while these technically are hyperparameters because they're things that you have to figure out a good value for in order to get your model to work, they're not really hyperparameters in the sense that like lambda 1, lambda 2, q, you know, which Q isn't even like a standard name for that. That's just what that's the letter that I literally chose to just say like, you know, the number of hidden units you have.
Okay.
It's so eta and your number of epochs, these are not actually hyperparameters in that same sense because those are things that you have to fine tune just to get to the point where you know that your algorithm's going to work. You know that your algorithm actually is going to converge when you run it, but it's not really going to get you like different results. You know, it's not like you're going to be like, you know, oh man, my trained model is like so much better with this value of eta versus this other value. It's just kind of like, if I have a really low learning rate, it's going to take a lot longer to train my model. If my learning rate's higher, I can train my model faster, but if I have it too high, then I'm actually my algorithm isn't going to converge at all. It's gonna diverge, right? So it's like that kind of you have to figure out because like it's going to make your model either work or not work, but it's not going to like tweak the performance at all. You know what I mean?
Yeah. Okay.
So
Let's see.
Yeah.
That makes sense.
So yeah, you wouldn't include like your epochs and your learning rate in your grid search if you are going to do it that way. You would figure out what those need to be just to make it so that the model trains, right? Just to make it so that your algorithm works, and then you would use those values that you found to then, you know, train your model with different values of lambda or like whatever. So like then you would use those values to just run your grid search and you keep training your model over and over and over again using these different things. And so yeah.
Makes sense.
It gets to be kind of a beast. It gets to be kind of complicated too, you know. Which is also sort of why, if you can solve the problem without going this far, you really want to.
Mm.
You know what I mean? Like, because this is just a fucking mess. Like, by the time you get to this point, there are so many moving parts. It's just it's so hard to find like just the perfect alignment of like everything, right? Like, it's sort of like, oh, I don't know. You guys maybe wouldn't be able to like relate to this, but like, you know, you get like your first like synthesizer ever and it's got like a couple of knobs, you know, and then like you go over, you know, to like you go into like the music shop to look at like something else, right? You're like, oh, I think I've outgrown the synthesizer, I want to like, you know, go to the next thing, and they're like, yeah, right this way, and they take you in the room with all the synthesizers and you go into like all these modular things where literally it's like not even one thing, it's like you're buying all these modules and you literally could fill an entire wall with modules that could have like patch cables running everywhere and all these like different knobs and everything. And you're kind of like, whoa, holy shit, like it just kind of like blows you away. So going from like logistic regression to an artificial neural network is kind of like that. Like it's like, it'll work, it can work really, really well, but you better know how to dial everything in. You know what I mean? Like,
Yeah.
So it's kind of like that.
In terms of like the scale of model flexibility, this one then is like pretty not flexible.
Oh, it's extremely flexible, and it can do anything, which is why neural networks are like the cutting edge,
Yeah.
right? But it's also like, I mean, this is why banks and Facebook and Microsoft and all those guys, this is why they hire like teams of PhDs to build these things, and why even those guys, like you have like teams of like 10 PhDs that take like 3 to 5 years to develop like a neural network model that like just really, really runs and just really, really nails this one task that it's supposed to do, right? Like, and that's why so many people are so keen to use APIs like Google Speech and stuff like that, like for voice recognition, because it's like, you know, it's like 0.6 cents to have it recognize or parse like a 15-second audio clip. And that's just so much cheaper and easier than hiring a team of 10 PhDs to spend the next 3 years building one for you, you know?
Yeah.
So that's why that kind of thing is the way that it is, right? Because it's like, these things are amazing. They really are. They truly are like amazing, amazing, amazing technology. An amazing mathematical technique. And it's more than just math even. It's like a convergence of so many different disciplines and ways of thinking. It's computer science, it's computational neuroscience, it's like, it's mathematics, it's like so many things. And it's really like a true like achievement in human history. But it's so complicated, you know what I mean? Like there's just so much to fine tune to really make sure you've like dialed in the best version of your model, So a thing that might have taken you weeks or maybe a couple of months to like fine tune, and make sure you found the best possible version of some other model. Now literally could take you years to dial in like the best possible combination of things for your neural network.
Yeah, just the minimum things. Just it sounds like a pain in the ass.
Yeah. And this is just, so also, if you think about it, for every hidden layer you have, right, that's another hyperparameter, right, because you have to now decide how many neurons does this hidden layer have to have, right? And it could be that the best combination is to have like 12 in this layer, 7 in this layer, 9 in this other layer, 2 in this other layer, and you have to figure all that out. And
imagine how many combinations there are.
Yeah, and you can't just, you can't just like go with your gut. You're a data scientist. You need to use evidence and data to back up what you're doing. And I mean, so you have to run all these diagnostics to figure out like what was the best combination of numbers of neurons in each layer to get the best result out of your model. Okay. Yeah. So it can be a little daunting. But if your client actually understands what they're getting themselves into by hiring you to build a neural network, it's also quite a lot of job stability that comes with this because God knows how long it's going to take you to build it. Like, you know what I mean? So, all right, I got to get out of here.
Okay, yeah, have a nice one.
So,
see you, man. Have a nice weekend.
See you later.